This lesson is an introduction to circular motion, where you'll learn to define and work with angular displacement, velocity or speed, and acceleration, and relate the linear or tangential motion of a point to its angular motion. First, let's start by defining the angle theta in radians that we sweep through as we go around a circle. Let's imagine we start there and we sweep around to here. So we're sweeping around the circle like that with our radius, and we trace out an arc of length s. If the radius of our circle is of length r, then the angle theta is just the ratio of those two, the ratio of the arc that we've swept out divided by the radius. So this would be theta in here. In other words, to trace out an angle of 2 radians, we would need to sweep out an arc that is twice as long as the radius. Rearranging this, we get that the arc length is equal to r times theta. Let's just take a look at the units for a moment here. The arc is a length, so it's in meters. The radius is also a length, so it's in meters. And theta is in radians, and it looks like that should give us meters times radians, but radians is kind of a non-unit that doesn't actually count for anything, so we just get meters equals meters. Once again, the angle theta in radians is the arc length divided by the radius. Now, just like we have linear displacement, linear velocity, and linear acceleration, we can also talk about angular displacement, angular velocity, and angular acceleration. So just recall in the linear case, displacement delta x is equal to position 2 minus position 1, and it's going to be in meters. Well, similarly, angular displacement, we'll call that delta theta, is equal to the final angle that we are at minus the initial angle that we are at, and it's going to be in radians. Velocity in the linear case, let's say we're talking about average velocity. Average velocity would be the overall change in position, or the overall displacement, divided by the time it takes to do that, and that's going to be in units of meters per second. Well, similarly, we can find the average angular velocity. Angular velocity, or angular speed, is given the symbol omega. This isn't W, this is a Greek symbol omega. So if I put the average there, I've got average angular velocity, or this could be average angular speed if I ignore the direction, and that's equal to delta theta over delta t, or theta 2 minus theta 1 over time 2 minus time 1. Units of the numerator are radians, denominator seconds, so this is in radians per second. So the average angular velocity is telling me how many radians am I sweeping out per second as I rotate around that circle. Similarly with acceleration, the average acceleration in the linear case was equal to the change in velocity divided by the change in time, and that was units of meters per second squared. Dividing here again by seconds, if I want to find the average angular acceleration, I give that the symbol alpha, another Greek letter. The average angular acceleration is equal to the change in angular velocity, delta omega, divided by delta t. And again, that's going to be equal to omega 2 minus omega 1 divided by time 2 minus time 1, and that's going to have units of radians per second squared. So that's an introduction to the different quantities, and we'll use them in some practice in a moment. But before we do that, we can also define the period, which we give the symbol capital T, and the frequency. The period is asking us the time to complete one cycle, or the duration of one cycle. And so it's going to have units of seconds. Again, it's the duration of one cycle or one rotation, and so it's going to be in seconds. Frequency is the opposite. It's telling us the number of cycles, or the number of rotations, in each second. So it's going to have units of cycles per second. Now, cycles per second, the cycles is not actually a unit, so that's really just equal to per second, or seconds to the minus 1. And seconds to the minus 1 has a special name. We call that hertz. So the frequency is given in cycles per second, which again is really just per second, and we call that hertz. Notice that these are reciprocals of each other. the time to complete one cycle, or the seconds per cycle, and the cycles per second are reciprocal. So the relationship is that the period is equal to 1 over the frequency, or vice versa. Also notice that if we have a constant angular speed, or if we're looking for the average angular speed, then we could say, well, I go all the way around a circle in 2 pi radians, and if the time that it takes to do that is 1 period, capital T, then omega, and I could really call that omega average, is equal to 2 pi over capital T. In other words, 2 pi radians divided by the time to complete one cycle. And because T is equal to 1 over the frequency, period is equal to 1 over the frequency, the angular speed is also equal to 2 pi f. So there's 2 more relationships for you. Now if we start from the relationship that we defined above, the definition of the angle theta in radians, which is this, we can relate each pair of linear and angular quantities. So if this is true, then the change in the arc length is equal to r times the angular displacement. And so if I wanted to find a formula for the average linear speed, that would be equal to delta s over delta t, which is equal to r times delta theta over delta t. I've just replaced this with that from over here. Now this is our definition for omega, or average, in this case average angular velocity. And I'm working with the averages, but the same would hold true for the instantaneous velocities. So that means that the average linear velocity is equal to r times the average angular velocity. Similarly, if I wanted to find the average linear acceleration, the average linear acceleration is equal to delta v divided by delta t. Well, delta v is equal to r times delta omega over delta t. That's what I've just shown over here. And now this is equal to alpha, my angular acceleration. So the average linear acceleration is equal to r times the average angular acceleration. And again, the same would hold true for the instantaneous values as well. Let's take a look at an example. We've got 2 children, Albert and Bobby, seated 1 meter and 2 meters from the center of a merry-go-round. So if this is the center, Albert could be here and Bobby is over there. And it's rotating steadily at completing 1 revolution every 5 seconds, and we're asked to find a number of things. So first, find the period of rotation. Well, the period of rotation, t, is going to be the same for both of them. It's just 5 seconds. And the frequency of rotation, symbol f, is the reciprocal of that, or 1 over 5 seconds, which is equal to 0.2 seconds to the minus 1, or 0.2 hertz. And again, that's the same for both of them. The angular speed, symbol omega, is constant here, and that's asking us to find how many radians they're tracing out per second. So they're tracing out a full revolution, or 2 pi radians, every 5 seconds. So I take 2 pi divided by 5 seconds. Again, 2 pi divided by the period, and that equals approximately 1.3 radians per second. And that's the same for both of them. They're both doing the same, tracing out the same angle. And that's what's key about angular speed here. It doesn't matter where they are on that merry-go-round, they have the same angular speed. That's not true of their tangential speed, which we could call v, or we might call v sub t. Remember that their tangential speed is equal to the radius times their angular speed. And the radius is different for each child. For Albert, this is equal to 1.0 meters. So we take 1.0 meters, we multiply it by 1.3 radians per second, and the radians is not really a unit, so we end up with meters per second. We get 1.3 meters per second. However, for Bobby, we're multiplying 2. The radius is equal to 2 meters for Bobby by 1.3, and therefore we get 2.6 meters per second. So when working with rotation, it can be helpful to use angular speed because it's the same no matter where you are on the rotating body. That's not true for tangential speed. Angular acceleration, which we give the symbol alpha, is 0 in this case because they're moving at constant angular velocity. And their tangential acceleration, a, or we could call that a sub t, is also 0 because their tangential speed is not changing. We could ask a different question, though, where they do have an angular and tangential acceleration. So let's say they start from rest and they speed up steadily over 12 seconds until they're completing 1 revolution every 3 seconds. Well, here, their initial angular speed is equal to 0, and their final angular speed is equal to, again, we do 2 pi divided by the period, which is equal to 2 pi over 3 seconds, or approximately 2.09 radians per second. Their angular acceleration alpha is going to be equal to the change in their angular velocity divided by the change in time, or 2.09 radians per second minus 0 gives you 2.09 radians per second, divided by 12 seconds, and that gives you approximately 0.17 radians per second squared. And again, that's going to be the same for both of them because they had the same initial and final angular velocities. So that's 0.17 radians per second squared for Bobby as well. Tangential acceleration, however, is going to be different. Albert's tangential acceleration is going to be equal to 1 meter. That's the radius multiplied for him, multiplied by 0.17 radians per second squared, gives you 0.17 meters per second squared. But because for Bobby the radius is equal to 2, the tangential acceleration is equal to 2 times 0.17 radians per second squared, and that gives you 0.34 meters now per second squared. So again, because Bobby is further out, he experiences a greater tangential acceleration. So that's an introduction to angular displacement, velocity, and acceleration.